So, as a continuation from our previous class, remember, previously we managed to work with the transverse waves. All right, remember, you were working with the transverse waves. All right, where we said a transverse wave is the wave in which the particles of the medium vibrate. So, take note, they'll be vibrating at right angles, which is at 90 degrees to the direction of motion. And we saw something that is common throughout, forming a wave of that length, of that nature. All right. So we want to note the difference between these two. All right. Because now we are dealing, or we are working with what we refer to as the longitudinal waves, which in this case, a longitudinal wave is a wave where the particles of the medium vibrate. How do they vibrate? They vibrate parallel to the direction of motion of the wave. This one, they are parallel to the direction of motion of the wave. That is the most important part that you're going to notice. So a practical activity that we can notice this, how to actually have these longitudinal waves, how to generate something like that, okay? If you take a slinky spring and hang it from the ceiling, pull it free, all right? Pull the free end of the spring and release it, all right? You put it on the ceiling, then you pull it, then you release it. Okay. What you're going to notice on that spring, it is that it is going to have a sort of a deformation, which is not the same throughout. There is a part that is going to be stuck like this, all right? Then there's a part that you're going to have separately or freely separated from one another. So in this case, it is different from what we had whenever we are to describe a longitudinal waveform, or a longitudinal wave. We are supposed to think of something of this nature, right? So you see this part here, very close to each other. Here, separate, very close to each other, separate, very close. That is what is important for you to note. So that is parallel. They vibrate parallel to the what? To the direction of motion of the wave. So noticing this, we are going to see this part here is referred to as the compressions. This part here, where it is very, very close to each other. That is the part of what? Of compression. All right. So let me not write on this one. Let me just show you this one so that it can be easier for us to explain these two terms. The region where the medium is compressed is known as the compression. So we're going to have the compression. That is a region of high pressure. This part of compression, all right, is a region of high pressure. That's a region of high pressure. Of high pressure. All right, that is the condition in the longitudinal wave. So you see here where they are very, very close to each other. These are the compressions. All right. Then we have got a region which is referred to as the rarefaction. This is the region where the medium is spread out, right? A region of low pressure. That is a region of what? Of low pressure. A region of low pressure. So they've got low pressure on the rarefaction. So these are the rarefactions. This one, right? Those are the ones that are being indicated there. Okay, so you need to be very careful with this part. And we're going to look into these questions. But before we look into these questions, we are going to notice that as you are working with the longitudinal waves, guys, the formulas will still be the same as what you had before when you're working with the transverse waves. Remember, you're working with the speed of the wave. Remember, when you're dealing to the speed of wave, all right, which is V, which is given from frequency times the wavelength, which is our lambda, this one, measured in meters per second. That part is still the same. The frequency, but what is the wavelength this time? In a longitudinal waveform, what is that you refer to as the wavelength? This one, our wavelength. In a longitudinal wave, that is the distance between consecutive points that are in the phase. That is, for example, two compressions or two rarefactions. What am I trying to say? The wavelength is taken between two consecutive points, like this one. Let's consider the way that it is here, the way that it is on our diagram here. That is the best way to describe wavelength. From a compression to another compression, that is a wavelength. From one compression to another compression, that is a wavelength. Or from one rarefaction to another rarefaction, that is a wavelength. From one point to another, which is consecutive points, all right? Compression to compression, then the rarefaction faction to a rarefaction. That is the condition that is important. The amplitude being the distance from the equilibrium to the position of medium to the compression or the rarefaction. That is what you are going to be having as the amplitude. So you see those terms as we had, nothing is going to change. All right, so nothing is going to change there. You just have to consider like the type that you're working with and consider how to take your values properly. All right. So talking about the wave speed, said that is the distance a wave travels per unit time. So if it is the distance per unit time, therefore velocity can be taken as distance traveled because it's distance per unit time. So it can be distance traveled over what? Over time taken. Over time taken. All right, this time is supposed to be in what? In seconds. The distance is supposed to be in meters. All right, this is supposed to be in what? In seconds, so that we obtain meters per second for the speed. So we can use the formula, which is the frequency times the wavelength. We can use this part. All right, if we are referring to the distance, we can refer it from the wavelength. All right, we can also write it this way. We can use the wavelength and the period. So it can be the wavelength over the period. All right. You see this one. So it can be the wavelength over what? Over the period. So whether you're given that, you're going to substitute your values, all right, to find whatever that you're given. Remember the T, which is our period. We talked about this period, all right, from our previous class. Remember, guys, T is equal to what? 1 over frequency. You're also given this formula that is measured in what? In seconds. So that is the condition. So once you take these into consideration, guys, you're not going to have a problem. And be careful on this part of the wavelength here. All right. So my lambda, guys, it is a little bit, okay. This is our wavelength. We must be very careful on the wavelength there because I'm saying it must be a condition that a compression to a compression. So let's say we've got the part of compression, then the part where they are separately, guys, this thing of drawing. All right. Then we've got a compression. So it must be a condition where you take a compression to compression. The distance in between becomes your what? Your wavelength. Or it can be from a rarefaction to another rarefaction where they are differently provided. That is the idea of what? Of the wavelength. Okay, so you must be careful how to take out, especially when you are given a diagram. It's not always when questions are of this nature in a theoretical manner. You can be given questions on a diagram. We're going to look into that. That will be our next class. We are going to look into question papers so that we can see how they do ask these questions. It's going to be easier, guys, as we are working with question papers. You will see. All right, so let us consider these two questions that we are given. All right, so the first part we have that we are given, let's just try to take our information. A longitudinal, we are told that it's a longitudinal wave. Here's a compression to compression distance. Take note, compression to compression. all right? Like this one, all right? Let me just take on this one that I actually have this one so that you can properly see. From a compression to a compression, or from a rarefaction to another rarefaction, what is the condition of that? What are you given? They are simply giving us the wavelength from one compression to another, or from one rarefaction to another rarefaction. It is the wavelength, all right? So we are given the wavelength, which is 10 meters. It takes the wave 5 seconds to pass a point. Take note, it takes the wave 5 seconds to pass a point. The wave, when it is moved, it takes 5 seconds. So you can refer that one to our time, all right, which is 5 seconds. So the question was, what is the wavelength of the longitudinal wave? What is the wavelength? What is the wavelength? So the wavelength is already given. It's already the one that we are given from that information. The compression to compression distance. So the wavelength we are already given. That is what? 10 meters. So the wavelength, guys, it's lambda. Okay. You see, guys, this software is, we won't be seeing where you are writing. So it will be something else, but that is the case there. Just, I don't know the way that you present it. Just try to present it in a nicer way. So lambda is just a Greek name. This one, lambda. It's just a Greek name to represent the wavelength. All right, do not worry about that. Then the speed of the wave, given the wavelength and also having the time, which is our period. In that case, we are going to calculate the speed. All right, so that is the part B. Remember, I said speed, which is V, is equal to the what? The distance over time. So meaning to say that is the wavelength over our time. That is 10 meters. Remember your wavelength and the time 5 seconds. So that was going to give us 2 meters per second. That is the condition of your question. All right. So everything was clearly given. On question number 2, you're given a flute produces, all right, a musical sound traveling at a speed of. So according to this information, we are given the speed of the sound of 320 meters per second. All right. The frequency of the note is, we are given the frequency of the note, which is 256 hertz. Calculate A, the period of the note. What is going to be the period? All right, so how can we determine the period from the information that we are given? Remember, period T can be calculated if we've got frequency. The frequency is already there. From our previous class, we saw this, that T is equal to 1 over F, 1 over frequency. And in this case, the frequency is given. So we are going to calculate our period, which is measured in what? In seconds. So that's 1 over the frequency, which is 256. So you can even write it like that, 1 over 256 seconds, or as a decimal. So as a decimal, it was going to be 0.003, and like that. There are so many. There are like 2 zeros there. So you're going to even have it like that, 0.039 seconds, or just leave it as a fraction like that. It is still okay to leave it as a fraction. So these are some of the typical questions that you might be given, just like the basics. Then the wavelength of the note, all right? The wavelength, if we are to consider, right, according to our information, that is the wavelength can be calculated. All right, so this is direct, guys, because we have got the frequency, all right? The frequency is there, but all right, let us just make the subject of the formula. Remember, V, the one that we are given here, is given as a frequency times the wavelength. So if it is a frequency times the wavelength, therefore we can make the wavelength the subject by dividing by what? By the frequency, both sides. So it means the wavelength is equal to the speed over what? Over the frequency. So thus we can calculate our wavelength by substituting. We already have all these values, all right? The speed is already there, 320 meters per second over the frequency, which is 256. We are given the frequency. So that was going to give us the wavelength, not the units, guys. The units of measurement. All right, so this is measured in meters. So it was going to give us 1,25 in meters. Just like that. So the information was direct. You are already given these values, so it was just a matter of substitution. So I want you to go through these notes. Just try to add one or two of what you already have. Maybe you already have these notes. Just try to add some of the examples. And like I said, we are going to be working with typical exam questions so that we just see how are they going to be asking these questions on our wave that is working on all this part of waves, sound, and light. All right, so that's it, guys. Till we meet again.